And what we see is what we saw before, which is that the values are displayed packed together without even a space in between each value. Next, in the red copy algorithm, where I'm using the output stream iterator with a space delimiter, we see that we get the values separated with spaces. And then finally, on slide 9, here is the output stream iterator with a new line delimiter. And in this case, each of the values of output gets displayed, followed by a new line character. The remainder of the program is here on slide 10. Here I have two empty decks of doubles, D1 and D2. Into D1, I'm using the front inserter so that for all the values from VBEG up to but not including VEnd, we're going to compute the square root, and the result is going to be inserted into the front of DI, so that when I display DI using the OStream iterator for doubles with a space, what I get out are the square roots of the values in the vector V, but in the opposite order. So I get 3, which is the square root of 9, as the first value, 2, which is the square root of 4, as the next value, and this is because we used the front inserter as opposed to the back inserter, which would have put things in the same order that they are in the vector V. In the second transform, we're executing the sine function on each element starting from VBEG and going up to but not including VEnd. Again, we're using front inserter, but this time to insert the values into D2. And so what I have for this blue line of output is the sines of all of the values in the vector V, but again in the reverse order of those values in vector V because of using the front inserter. Now here in the bottom of slide 10, we're sneaking in a different version of transform. The version of transform that we've been using up to now takes one input range and an output iterator. In our case, we're using a front inserter as our output iterator. But there's another version of the transform algorithm that takes two input sequences. Here's the first input sequence, d1.begin up to but not including d1.end. And we can also specify a second input sequence. Here we're specifying d2.begin as the beginning of our second input sequence. Now the assumption of the transform algorithm here is that D2 contains at least as many elements as exist between d1.begin and d1.end. What we're doing now is we're executing a binary function. The pow function computes x to the y power, so it has two operands. X is the left-hand operand, y is the right-hand operand. So the x values are the square roots taken from D1, and the y values, the power values, are the sines taken from D2. And so what we're doing here with pow, in effect, is computing some square root to some sine power. And all of that output is going to the output stream for doubles with a space in between. Okay, so 1.57264 is 3 to the 0.412118 power, etc. Okay, so it's very handy to know about the second variation of the transform algorithm that takes two input sequences and uses a binary function to produce one output sequence of values. Next up, we're going to take a look at function objects. A function object is simply an object that implements the function call operator, the open and close parenthesis. You can overload the function call operator for a class in the same way that you would overload something like assignment or a quality test. Here we have an example on slide 13. This is a class named addN. It has one private data member, which is the int value n, It has a constructor that takes one int as an argument and sets n to that integer argument. And then it has a function call operator. And this function call operator takes one argument, which is an integer. In the definition of the function call operator, we're using j as the name of the parameter. And this function call operator is going to return j plus whatever the number n was as its result. We can use a function object in algorithms like for each and transform in the same way that we could use ordinary functions or function templates that we've talked about before. Here on slide 14, we have an example program making use of the addN class. First, we have our vector of int v, initialized with 471349. We're using copy to display the values of v. The output is on slide 15. All right, so that first line of output is the contents of v. Then we are creating an object add3, which is an addN object with 3 as its initial value for n. D here is an empty deck of double, and in this blue transform algorithm, we're reading as input the values in the vector v from begin up to but not including end. We're inserting the result into the deck D at the back, and the operation we're performing on each value coming from v is add3. All right? So a value is going to be pulled in from the vector v. Add3 is going to be performed on that value, which will result in that same value plus 3. And that same value plus 3 is what's going to be inserted into the deck D. Consequently, when I display the deck D using copy with an OStream iterator, what I get out is the same values that are in V except with 3 added to each one. So instead of 471, I get 7104, and so forth. Now, one of the convenient things about having a class with a constructor is that you don't need to create a named object like add3. You can simply call the constructor in your transform algorithm to create a function object on the fly. In this case, the function object is going to subtract 6 from each value coming through. This transform is still reading from the vector v as its input values, but notice that we're using back inserter on D to add these values to the back of what's already in D. Okay? So in the blue copy, we saw that deck contained the same number of elements as V, but with each of the elements 3 greater than the elements of V. Now we're going to have 6 more values inserted at the back of D, which are the values of V minus 6. So 4 minus 6 gives me a minus 2, 7 minus 6 gives me a 1, etc.